Okay, we're going to be talking about parameterized solutions today. And basically, parameterized solutions are vector form. We're going to put the solutions in vector form, and let me show you a little bit about how that's going to go for us. All right. So we have example one, and by the way, example one is from the course notes. All right. So this is section 1.3 and example one, and I'm using this example matrix A right here. Okay. So example one, um, and we have this row reduced matrix, and can we solve it? And so this a question I've had, well, yeah, we can solve it because we actually know what x3 is equal to, the bottom row. So once we have it in, have a matrix reduced to REF, then we can start at the bottom and work our way up with a process called back substitution. Okay, so that's what we're doing here. And the bottom row basically tells us that negative x sub 3 equals 2 or x sub 3 equals negative 2. Now the top row has free variables in it, so let's remind ourselves, right? So basic variables correspond to the pivots, all right? So we're going to have two basic variables, x sub 1 and x sub 3, but this variable x sub 2 does not correspond to a pivot, so it's a free variable. It's going to be a variable that we are going to have to deal with, all right? Well, when we take the top row, all right, and we have negative 2x sub 1 plus 2x sub 2 equals 6. We divide through by 2. And then um, it depends on how you want to think of this. I actually multiplied through by negative 1, right? So all of those flip sign. And then I subtracted at that point x sub 2 from both sides. I'm sorry, it would have been negative, so I added x sub 2 to both sides. There we go. And so x sub 1 equals x sub 2 minus x sub 3. So yeah, there is, I'm sorry, that got a little confusing doing that all in one step. But I did multiply through by negative 1, and then I moved the x sub 2 over. And since it was negative, I was adding x sub 2 to both sides, which should explain how everything arrived. And so then what do we have? Okay, so notice that we know exactly what x sub 3 is, and we know that x sub 2 has this, x sub 1 has this free variable x sub 2 in it. Okay, and when we put that together, right, so this is just the top row, right, x sub 1 is equal to negative x sub 3 plus x sub 2. What is x sub 2 equal to? Well, x sub 2 is a free variable. It's just equal to itself. It's just whatever that real number is. And then x sub 3 we know has to be equal to negative 2. All right, so then the first part, these constants correspond to a vector. Negative 3 is 0, negative 2 are its components. And then these also can correspond to a vector. Right? We just put in the real number x sub 2 and the real number x sub 2 and 0, right? There's nothing here. There's nothing in this area. So that's a 0. Same in here, right? So for these areas where we don't have anything, we just put in a placeholder, a 0. Okay. Are we done? Not quite. So what we usually do with this final vector is that we factor out the x sub 2. It's just a real number, and so we factor that out. Okay, and I'll show you in a minute, we often do use a variable like t, sometimes v, sometimes rs, if we have several of them, rs and t, uv and t. Why do we use those? Well, they're just real numbers. Okay, so this is just saying, look, I can multiply any real number x sub 2 times this vector, and it will be a solution. Okay, so there are infinitely many solutions, and this describes them. Again, we sometimes get rid of the x sub 2 and use another real number, and we'll talk about that in a moment. So let's talk about example 2, where we have matrix B and we row reduce it to this form. And again, in the notes, right, it actually gives the steps. Sorry. In example 2, it actually gives the steps here. So you can use this as practice. And this is the original, or this is the matrix we're looking at. Okay. But what's happening? Well, look at this bottom row. This bottom row is saying that 0 times x sub 1 plus 0 times x sub 2 plus 0 times x sub 3 equals 1. And I can write that out, but what I'm getting is 0 equals 1. And we're like, what? Oh my goodness. 0 cannot equal 1, so what does this mean? Well, this means that there are no solutions, right? So remember, with a linear system, I can either find an exact solution, I can find exactly one solution, I can find 0 solutions, or I can find infinitely many. So example 1 showed us what happens when we have infinitely many and we put it in parameterized form or vector form. Here, we're not going to put anything in vector form because we have no solutions, right? So there are no solutions. I'll just put in none because I have trouble writing with the mouse. All right, no solutions at all. Okay, and I'm getting rid of the ink. And when we have a clearly false equation, so we do the row reduction, and then we start in on our back substitution, right? So back substitution, we solve the bottom equation first, but we got to here, we're like, so we put on the brakes, and that indicates no solutions, all right? So example 3, we have a matrix and we have row reduced it to REF. And let's talk about the back substitution. Okay, so we're going to start on the third equation, the 5x sub 5 equals 5. We'll just divide through that equation by 5, right? And we just get that x sub 5 equals 1. That's good. And then the middle row has a free variable. So remember, so the basic variables are going to correspond to the pivot columns, all right? The variables in the pivot columns, and then we're going to have 2 free variables, right? So the x sub 2 and the x sub 4 are going to correspond to free variables. And so the second row has a free variable in it, and what we do is we solve the basic variable in terms of the free variable, right? So the equation basically says x sub 3 plus 5x sub 4 equals 1. We subtract the 5x sub 4 from both sides. So x sub 3 equals 1 minus 5x sub 4. Hooray. What next? Let me get rid of the ink here. Okay. So what we've solved so far is we did back substitution and we made it up through 2 rows, right? But we still need to solve the top row. But this is what we got from the back substitution, doing the bottom row and then the middle row. And so the final basic variable we have is x sub 1, and we have this big equation 3x sub 1 minus 3x sub 2 plus 9x sub 4 equals 6. And we can divide through by 3. Every single one of the coefficients in this equation is divisible by 3. So when we divide through by 3, we get that middle row in the string of equations. And then we're going to add x sub 2 to both sides and subtract 3x sub 4 to both sides, from both sides. And yeah, so we end up with x sub 1 equals x sub 2 minus 3x sub 4 plus 2. Yay, we're moving right along. And what happens next? Well, I want to point out that the textbook, when it's parameterized the solutions, it uses row vector notation. Okay, and it's exactly the same, the first component, the second component, the third component, and so on. I just find it a whole lot easier to read in column vectors. Okay, it's the same thing. Now, I did factor out the free variables, but I basically just took this row vector notation and went to column vector notation. And you can see that. How? Well, let me get rid of these. First thing I want to note about example 4 is it's not in the online notes that we have. Okay, so I'm going to open up MATLAB and MATLAB Online, and I'm going to work in there. Okay, so here we go. MATLAB Online in the live editor, and I have the matrix typed in and ready to go. And let's change that. So I do like to have the matrix inline. Again, you can see the little icons over here. You can change that to your preference, and I've switched to mine. Okay, so the first thing we need to do is we need to get, we have a 1 in this pivot position, or a -1. So we need to get a 0 below it, all right? And how are we going to do that? Well, the first thing I'm going to do is little d equals capital D, right? So I'll leave the matrix capital D unchanged by working with the lowercase d matrix. And I'm going to take row 2 and I'm going to replace it with itself plus row 1, right? If I add the -1 and the +1, I'm going to get a 0. And so I'm going to replace row 2 with the sum of itself in row 1. And again, sorry, I usually put some spaces in here just to make things visually easier to see. And I'll get rid of the ink. So we're going well so far. And now what I'm going to do is I'm going to take row 2 and divide through by 2, right? So D2, the second row of little little d matrix is going to be itself divided by 2. Again, you can think of this as multiplying through by 1/2 or dividing through by 2. Either way works. Okay. So now we have solved this thing down to REF form. Okay. We've solved it down to REF form. By the way, if you want to make your life a little easier, we could multiply through the top row by -1. Again, having a +1 as the pivot does make life slightly easier, but I did not do that in the notes. So noting that we've got this, right? So we've got this row reduced matrix. It is in REF. And so now it's time to back substitute, right? Once I reduce to REF, I can solve. I don't have to go all the way to RREF. I can solve these by going to REF and using back substitution. Okay, so let's take a look. And I did bring up here the same exact matrix, right? I had row reduced to here. I did not multiply through by -1. And solving the bottom row, we get 4x2 plus x3 equals 2. And then we subtract x3 from both sides, and then we divide through by the 4. So that's x2, right? So 2 divided by 4 is 1/2, and minus x to the third, x3, sorry, minus x3 over 4. Okay, so we know what x2 is equal to. Get rid of the ink and slide forward. Get rid of the ink. All right. So if we've got the second row, right, x2, we already know what x2 is. And here I did multiply through by the -1, right? So I have positive x1 minus 4x2 equals -3, right? So the negative here and here are when I multiplied through the top row by -1. And that's why this is positive. Okay, so then I just have to add the 4x sub 2 to both sides. And now there's something interesting. I'm going to get rid of this ink so you can see, but take a look. What is interesting about this? Well, the interesting thing is I know what x sub 2 is equal to, okay? And so I can substitute it in right here. And so I can simplify this top row equation by substituting in the second row. Even though it still has a free variable in it, I can substitute in for the basic variable here and get things to be a little simpler. Okay, so when I do that, I just plug in what x sub 2 is equal to, and then I have a 4 outside, which cancels out the denominators, right? So 4 times a half is 2, so negative 3 plus 2 is negative 1, and then 4 times minus x sub 3 over 4 is just minus x sub 3. So we get a simpler equation for x sub 1 when we substitute in for x sub 2. Now, when do we want to do this? Oh, we only want to do this when it actually simplifies things. So now you're like, well, how do I know? How do I know before I start whether or not it's going to simplify things? Well, honestly, I looked at it and tried a little bit in my head and thought, oh yes, that is going to simplify it. And so I went ahead. So yeah, is there a little bit of looking ahead to see? Yes. You do not have to do this step, but it does simplify our answer when we do. So getting rid of the ink, we can step through and see, right, summarizing the simpler version of the equations and switching to the parameterized form or the column vector form, right? The constant vector is -1 in the first component and a half in the second component, and then we have this x sub 3. And I factored out the minus sign, right? You see there's a minus here and a minus here. So technically this could be a plus sign, but then I'd need a minus sign here and a minus sign here. And what did I do? I factored out the minus. So I have the minus a positive matrix, a matrix with positive elements. Okay, that is legit. You could also do the plus in the middle and the 2 negative components in that second vector. Either way is mathematically correct. I just think this is simpler and it looks nicer. And I keep saying visually appealing. Is it important to do mathematics in a visually appealing way? Well, what I mean by visually appealing is it just makes more sense to me. I do it in a way that makes more sense. Why? Because I'm less likely to make mistakes when visually the way it's set up makes sense to me. So I don't particularly like row vectors because visually I get a bit confused. So I switch to column vectors, and I do that for you guys too in these videos. Why do I go to column vectors? Because they make sense to me visually. What do you need to do? You need to do the thing that makes sense for you, your brain. You're the one who has to do this on a test or a quiz, so you should figure out whichever way is mathematically correct and makes sense to you. Okay? And then I want to show that, yes, we often take this real number and we make it something like t, RST, UVT. And so this real number that produces infinitely many solutions, right? So t can be any real number, and as I go through those infinitely many real numbers for t, I get infinitely many solution vectors x. Okay, so we have infinitely many solutions. Sorry, I struggle with the infinity symbol when I'm using the mouse, but we have infinitely many solutions, and now we've shown them in the parameterized form. All right, so this is what you're going to use on Lab 2, and good luck.